Hi, this is a review for Chapter 4, Applications of Derivatives. Let's begin with concavity and curve sketching. Here we have a definition. The graph of a differentiable function is concave up on an open interval if f prime is increasing there, and it is concave down if f prime is decreasing. The given function may not be concave up or concave down everywhere. However, locally, in subinterval, it can be concave up, and in some other area, it can be concave down. By using second derivative, we can figure out the concavity. Once the function is twice differentiable, and if f double prime is positive, that means that f prime is increasing, so that the graph of f must be concave up. And second derivative is negative, then the graph of f must be concave down. And here another definition, point of reflection is point where the concavity changes from concave up to concave down, or from concave down to concave up. Then the point is called point of inflection, or simply an inflection point. Second derivative can be used for recognizing local extrema. Okay, here, and we have 3 cases, f prime for every case. Now f prime at c equals 0, which means that c is a critical point. Now, at the point, second derivative is negative, then that means that here that is concave down, so that at the point, f has a local maximum. Now, once second derivative is positive, which means it's concave up, so that f has a local minimum at the point. Now, second derivative is 0, then we cannot use the second derivative test. Okay. Now, when you try to sketch the given function, then this is the procedure, and try to find the critical points through derivative, and also try to figure out the regions where the curve is increasing and curve is decreasing, and also try to find the points of inflection, and now try to determine the concavity. And along with that computations, you can find the key points. The key points can be the critical points and local maxima or local minima, and intercepts, x-intercept, y-intercepts, like that. And first try to plot these key points, and then sketch the curve together with asymptote, if any. Then you can make the graph very nicely. Okay, let's try to sketch the graph of a function here given, and now try to identify the local extreme, the points and inflection points and concavity. Okay. Now for function f, okay, let's begin with, let's try to find the critical point first. Okay, so that here now f prime, that is 4x cubed minus 12x squared, right? then that is same as now 4x squared, then x minus 3. If it is 0, then x will be 0 and now 3. These are critical points. Okay, so here already we put here for f prime. Now at x equals 0 and x equals 3, the f prime is 0. Okay, now we can specify the sign here. If x is smaller than 3, then f prime is negative. Okay, so that, and smaller than 3, then it's negative. Of course here negative, negative, 0 at a moment, and again negative. And then if x is larger than 3, then f prime is positive. Okay, here, now let's try to get f double prime. So that anyway, here at 0 and 3, it can have local extrema. Later on, we can specify after computing more around the inflection points and we'll figure it out later on. Okay, f double prime, then that is 12x squared minus 24x. So that is same as 12x, come on, so x minus 2. So if we set it 0, then x equal 0 and now 2. So double prime is 0 at 0 and 2. And here, if x is less than 2, then negative, right? Is less than 2, then double prime is negative, and at this moment it becomes 0, but again negative. But it's larger than 2, then it is positive, positive. Of course here that is also positive. Now, so we can find the key points and where here now 0 and 2 and 3. Let's try to find the key point, the value of f and at 0, 2, and 3. Okay. Once x equals 0, then we can easily see that here function value is 10. Okay. Now, once x equals 2, then f of 2 equal now 2 to the 4 minus 4, 2 to the 3, and plus 10. Okay, that is 16. Now, that is now, okay, 32, and here plus 10, so that is now minus 6. So at 2, the function value is minus 6. Okay. Now, when x is 3, so f of 3 is the same as, now that is 81 minus, that is 27 times 4. Okay, 4 times 27 and plus 10. Okay, that is 27 times 3, so that there's a minus 27 along with that, 2 of them, and plus 10. So it is minus 17. Okay. So we have here minus 17. So now here key points are when x equals 0, the value is 10. That will be again y-intercept, and x equal 2 then in minus 6, and x equal 3 then minus 17. Now let's try to look at behavior of f. F prime is negative, which means it's going down. Now double prime negative, that means concave down. We already know that from here. And second derivative is negative, then is concave down. Okay, so we can make here like that, it's going down, but concave down like that. And again here, that is going down, but here again, okay, it's 0, but anyway, it's going down again, the concave down. Now it's going down, but concave up. That means down, but concave up, like that. Now this is going up and concave up. So here, like that, right? So when you try to sketch the graph, then you can do in this way. Now it is x coordinates, and that is y. Oops. Can I start to make it better? Okay, straight line. Yep, much better. That's y-axis and that's x-axis. Now when x equals 0, the value is 10, and then x equal to 1, 2, 3, then the value is minus x. Okay, that is now here minus x, and when x equal to 3, then minus 17. Okay, we'll go down further over there, so that, okay, that is here, this point, that's minus 17. Okay, when x is less than 0, then go down and concave down. So here it is going down this way and going down. Just a moment. Right now, somehow I feel I made a little bit of a mistake. Okay. In fact, okay, x is there, so that now this is quadratic. So between 0 and 2, the value is negative. However, if less than 0, then it is positive. Okay, I'm sorry. That is, okay, if you try to make the picture for that, then f double prime is made in this way. So it's in 0 and 2. So there's y equal f double prime. So that here, between 0 and 2 is negative, but left over 0, it must be positive, right? Okay. So that one, by using eraser, yeah, that must be here now and down, but concave up way, so that like that. Okay. Sorry about that. Okay. So once x is less than 0, then down and concave up here, so that it's going down that way. And then between 0 and 2 is going down and concave down like that. And between 2 and 3 is down but concave up, so that is turning like that. And then after 3 is up and concave up. Okay, so we can make such a sketch, and we can easily see that that is inflection point of inflection. Again, this is inflection point, and that is again inflection point. Okay, this is local extrema minimum, but it looks like this is global minimum. Okay, global or minimum. Okay. In determinate forms and L'Hopital's rule. Okay, here in L'Hopital's rule, especially we are interested in the form of a fraction f of x over g of x, and as x approaches a, both of them may go to 0 or go to infinity or minus infinity. And one of them can go infinity and one of them can go negative infinity. It doesn't matter. But here, both should go 0 or both should go infinity or minus infinity. Then the limit will be the same as here now, the limit of the f prime over g prime. So you are making derivative both top and bottom separately and try to measure the limit of the ratio. That is L'Hopital's rule, sometimes called the Bernoulli's rule. Okay, let's try to solve this problem. Once x approaches 0, then now here this is approaching 1, now that is approaching 0. So numerator is approaching 0. And also easily we can see that the denominator approaches 0. So this one is 0 over 0 shape. So that is the same as same limit and derivative of this one. That is now 5x to the 4 and e to the x minus 1 plus now x to the 5 plus 1. Now derivative over e to the x minus 1 is same as e to the x. Now bottom, that is for this term, derivative is 2 to the x times natural logarithm of 2. And minus 1 will disappear. Now x approaches 0, then now that is this term will go to 0. But this one is now 1 and 1, so that numerator will approach 1. And now denominator, this is approaching 1. Now the remaining part is natural logarithm of 2. That's the final answer. For this problem, okay, theta approaches 0. Now cosine squared theta minus 1. Cosine theta is approaching 1, so that the numerator will approach 0. And also for the denominator, okay, it is approaching 1 and 0, so that again it's approaching to 0 over 0 shape. So we can use L'Hopital's rule. That is the same as now limit, the same theta approaches 0 and derivative. So that is now 2 cosine theta, and cosine theta derivative is minus sine theta. So we can put here minus. Okay, now divide by e to the theta is the same as e to theta, and theta becomes now minus 1. Once the theta approaches 0, then, okay, now sine theta is approaching 0, and e to theta will approach 1, so that again, now there is a 0 over 0 shape. So you can apply the L'Hopital's rule one more time. There's now limit, and we are making derivative for the top. But anyway, this top is the same as, okay, we'll do a little bit simplification. That is same as now minus sine 2 theta. Okay, same as that. So that now once you try to make a derivative, then that is same as minus, okay, cosine 2 theta. 2 theta derivative is 2. Okay. Now the bottom, that is e to the theta. Theta approaches 0, then that is approaching 1, and that is minus 2 divided by 1, so that is minus 2. That will be the final answer. Now we used some trigonometric formula for that, but you can do by using product rule, you can make derivative. And also here in the beginning, this portion numerator can be written as now minus sine and square theta. Okay? So that derivative of that is the same as this numerator. So you can do. And during the computation, if you can simplify, then you can do it using the trigonometric formulas. Okay, let's move on. Okay, other intermediate forms. Here, now originally, L'Hopital's rule is developed for the fraction. But here we have 0 times infinity, or infinity minus infinity. But for this one, once here x approaches 0 from the right, then that is 0 becomes 0, and that portion will become infinity. But this can be written in this way. There is a natural logarithm of x squared divided by here 1 over x. Then now it goes to infinity and again goes to infinity. So that is infinite over infinite shape. So now we can use L'Hopital's rule. So limit, okay, that is, okay, 2 can go out. Natural logarithm of x, its derivative is same as 1 over x. So that is 2 over x. And the bottom, there's minus here 1 over x squared. So that is the same as minus 2 and x. Right? So x is approaching 0, so that the value must be 0. Okay. This one, once x approaches infinity, then this term goes to infinity, and that one also goes to infinity. Now, for this one here, and you can combine them by using here the quotient rule. So that is same as natural logarithm, and 2x on the top, and on the bottom here x plus 1. That is the same as once the limit exists, then now this is continuous function. So limit and continuous function can be applied with change of order, so that can be written in this way: natural logarithm and limit x approaches infinity and 2x over x plus 1. We know that is approaching 2 divided by x, and so that we can see easily the limit is 2. So that there is a natural logarithm of 2. So that is the final answer. Okay, now here x is approaching 0 from the right, then this term is approaching 1, and now 3 over x will approach infinity. So this given limit has shape 1 to the infinity. And also over there, once x approaches infinity, then that is infinity and to the 0 shape. And once the given term is related with a power, then you may try to use logarithmic technique. So let's start with that is y. Then if we said y equal 1 plus x and x over 3, then take a logarithm, both sides, natural logarithm. Then here, this will be used as power, so that x over 3 and natural logarithm, okay, what is that? Natural logarithm and 1 plus x. Right? Okay, x is approaching 0, then this term is approaching 0, right? And so that here, x now for that one, okay, you can easily find the answer from this one. Now, okay, if we apply limit, then limit, okay, natural logarithm of y is same as that one is same as now limit of x over 3 and now natural logarithm of 1 plus x. But both of them is approaching 0, so that is 0. Quite easily we can see the value is 0. Okay. Oops. Okay, I'm sorry for that one. Here somehow, when I'm writing, here I made it too simple and I made over the mistake. Okay, let's eliminate this portion and let's do it again. I'm sorry about that. Here, y is now 1 plus x and 3 over x rather than x over 3. Okay, I'm sorry about that. Okay, now if you apply logarithm, then there will be x over again. Okay, 3 over x and times natural logarithm and 1 plus x, right? Yeah, now it's okay. Here we apply limit, then limit, and natural logarithm of y equal same as now limit. Okay, we have a 3 here. Now natural logarithm 1 plus x over x. So here now x is approaching 0 from the right, so that this will approach 0 again. Denominator will approach 0, so there is a 0 over 0 shape. So we can use L'Hopital's rule. So that is same as limit, and now 3 times the derivative will be 1 over 1 plus x. Now the bottom will be 1. So we can rewrite this one in this way. Limit and 3 times 1 over 1 plus x. Okay, so here that is now once x is approaching 0, then there will be 3. So that one is the same as logarithm limit of y. So eventually what we have to do is limit of y. That's what we have to get. But its logarithm is 3. So that here we can rewrite this portion. Logarithm of limit of y equal 3. That means that here the unknown, that limit of y is the same as e to the 3. Okay. Okay, same technique will be used for this problem. So start with y equal x to the 1 over square root of x. And we are taking natural logarithm. And natural logarithm of y will be here 1 over square root of x and natural logarithm of x. Okay, let's rewrite this one. Natural logarithm of x divided by square root of x. Now we apply limit. Okay, natural logarithm of y equal here limit. Of course here x is approaching infinity and square root of x on the bottom and natural logarithm of x. Now as x approaches infinity, this goes to infinity and also bottom goes to infinity, so that this term is infinity over infinite shape. So we can use L'Hopital's rule. Okay, so here the same limit, and that is 1 over x, and bottom x to the half, so half will come out, and x to the minus half. Right? Okay, so if we simplify this one, then there will be constant will be 2. X, okay, it's half power and power minus 1, so that x to the minus a half. Okay, is minus half and minus 1, so that x to the minus 3 over 2, right? X to the minus 1 divided by, okay, minus half, not minus 3 over 2, minus half. Okay, so once x is approaching infinity, then it'll become 0. So logarithm of limit y is 0, which means that that given term must be 1. So that if you are taking logarithm, then the value must be 0. So the 1 is the final answer. Okay? Applied optimization. And that is, the problems are given along with some story. And so that first of all, you have to understand the problem. In the problem, and here, you have to specify what are given and what is the unknown quantity to be optimized. And you have to introduce variables, and you have to express the quantity to be optimized as a function of a single variable. And by using derivative technique, you can find the optimal value. And mostly in your level, the optimization problem will be given with 2 quantities and 2 variables. One is the quantity to be optimized, and the other one will be used to express the quantity to be optimized as a function of a single variable. Yeah, let's see this example. The U.S. Postal Service will accept a box for domestic shipment only if the sum of its length and girth is distance around, does not exceed 108 inch. And what dimensions will give a box with a square end the largest possible volume? Okay, here 2 quantities are, one is volume, one is that length and girth sum, and so one is length related, the other one is volume. Okay, if we introduce the variable, so here in strategy, you have to introduce variables, and you have to understand what is given, what is the unknown quantity to be optimized. To be optimized in this problem is volume, right? And now here, first of all, you have to introduce variable. Let's say this is y and that is x. Okay, and square bottom and length, so that the volume will be x squared y. Now, another quantity is, now the sum of its length and girth is not exceeding 108 inches. It's maximum possible, the box will have here 108 inch. So that here, now girth will be 4x, and 4 sides along this, around the distance. And here, the length is y, then must be 108. So like this, most of a problem in your level, the optimization problem will be given with 2 quantities and 2 variables. Okay. Now, here you have to express the quantity to be optimized as a function of 1 variable. The easiest way is that y here can be replaced by using this equation. From this one, y is the same as 108 minus 4x, so that here v can be written here x squared, and y is the same as 108 minus 4x. So let's rewrite here. So 108 x squared minus 4, 1x squared minus 4x, x cubed, right? Okay, so we have to optimize that. Now v prime, that is the same as here 108 times 2, which is 216x minus 12x squared. That is same as, okay, that is 12x can come out, and there's 18 minus x. So x can be, if you set it 0, then x equals 0 and x is 18. But x is length here, side length, so that cannot be accepted. So only possible is 18. And you can check easily that when x is 18, the volume will be maximized. And here you see that now once it's smaller than 18, then the slope is positive, v prime is positive. And now once x is larger than 18, then slope is negative. So that here at 18, the is critical point n here volume must be maximized. Okay, x is 18, then from the equation, so that 18 and 72, so that it is 36. Right? Length is 36, and side x is 18. At the moment, the maximum volume is 18 squared 36. That is the amount. Okay. Now Newton's method. Newton's method is for finding 0. So that here we have to find x such that fx equals 0. And that's what Newton's method is used there. But in the beginning, we don't know the x value. So we may start with initial approximation. So let's say that is x0. Then, as you can see from the picture, we go to the graph and try to make tangent line. So that is exactly the tangent line, the slope point form of the tangent line here. And we try to find x-intercept by setting y equals 0. Then here y equals 0 and solve for x. Then that is here this point, and we'll say that point is x1 is improved, updated approximation. And we'll do this computation again and again. So from this one, we are making here the tangent line, and again try to find the x-intercept, and that's called x2, and again go to the graph and tangent line and x-intercept. So here mathematically we can write down the Newton's method in this way. In the beginning, we guess a first approximation, an x0, and now, and use the first approximation to get a second, and the second to get a third, and so on. So that is exactly the formula. Start from x0, and we are making x1. By using x1, we can get x2, and so on. As far as f prime at xn is non-zero, then we can update. And Newton method is working along with the assumption that here f prime is non-zero and x0 is really good approximation of the desired the solution, then it is convergent quadratically. Its convergence is so fast and it's very popular algorithm. Okay, here let's try to find and 5 to the 1/3 power applying Newton's method. If you compute here, then this is quite accurate to output. Now we'll use here, first of all, we'll try to specify interval where the solution might be. And by using intermediate value theorem, we can show that a 0 of fx, x cubed minus 5 is in between 1 and 2. Okay. Now, once we say, okay, this equation is made in this way. Once this is x, then now power 3, 5, and from this one, we define f of x equal now x cubed minus 5. So they're solving this equation is the same as that one, right? Okay, so f of x is given in this way. Now, part A, we will specify some interval having a 0 function f of x. Now, is 1, f of 1, then 1 minus 5 will be minus 4, and f of 2 will be here now 8 minus 5, which is 3. And at left end, the value is negative 4. At right end, the value 3. So that is continuous function. So there's somewhere between 1 and 2, the function value must be 0 by the intermediate value theorem. Okay. Now, part B, we run 2 iterations of Newton method to find x2. Start from x0 is 1.5. Okay, let's do that. Now, xn plus 1 is same as xn minus f of xn, which is xn cubed minus 5, and f prime xn, of course f prime is 3x squared, so that is a 3 now xn squared. Okay, let's try to simplify a little bit. Okay, that is same as xn now minus here xn over 3 and now plus 5 over 3, and on the bottom we have xn squared, 1 over xn squared. Let's rewrite this one. Then there's 2 over 3 xn and plus here 5 over 3 and 1 over xn squared. Okay. Okay, we'll use that. Here x0 is 3 over 2. From this one, x1 equal same as, okay, 2 over 3 x0 plus 5 over 3 1 over x0 squared. x0 is 3 over 2, so that 2 over 3 and 3 over 2 plus 5 over 3, and that is the square. That is the same as now 4 over 9. So that is 1, and that is 20, and that is 27. 1 plus 27, oh, no. That is 20 over 27. 20 over 27, that is 47 over 27. Okay, we found x1. Now for x2 equals same as, okay, that is the formula here. And 2 over 3 times x1 plus 5 over 3 and 1 over x1 squared. So that is 2 over 3 times x1 is 47 over 27 and plus 5 over 3 times 1 over x squared. So that that is same as 27 over 47 squared. Now it's not easy to compute by using pencil right now, so that you can stop here, or by using a calculator you can find the numeric value for that. Okay, let's see the computer output for this problem. Let's open here. That is Octave, and the directory is here. Now I made here Newton 5/3 root .m. Okay, that is now defined here. F of x is x cubed minus 5, and start with 1.5, and now 6 iterations. There's f prime, and the correction term is subtracted, and now after each iteration we can see the updated value and correction term, and at the moment f value. Okay, now we hit F5, then now in command window we can see that. Now start with 1.5, and after one iteration it becomes 1.740, and so on. And at the moment function value is 0.2. And after 2 iterations, so that is x2. So that is x2. And at the moment, correction value and f value, look at here, after 5 iterations, here you cannot see the meaningful digit, all are 0. And so then 5 or 6 iterations later, it will convert. It's so fast that you can find the value very efficiently. Okay, in our computation, x1 is 47 divided by 27. Okay, let's try to measure numeric value for that. 47 divided by 27. Okay, yes, short form. So now let's try to make a long format. And again, we write over there. And then now this x1 is the same as that, right? They are same, so it's correct answer. Okay. That's the end of chapter 4 review. Thank you.